Hello guys. So, there is some approach that you should know before going for the big interviews, right? So what I'm going to do, I'm going to do deep dive session for the binary search algorithms that we have already seen in the first part of this video, and the first program, that lead code 700, we have already covered, right? So in that approach we have seen the recursive, that if you develop this program, right, using the recursive approach, so when you go for the interview will ask you, can you please optimize this code, right? So this code is already a quite optimal for its purpose, but the search in a binary search tree has a time complexity, that is, we can say O of h. Being h is the height of the tree, means we will get O of h, right? Means we will not say O of n because we are talking about the tree, right? So height of the tree will start from what, like this, right? Like this. Okay, means it is we'll say 1 2 3, right? Like this we are saying height of the tree. So the, if you say time complexity is O of h, right, where h is the height of this tree. Okay, balanced tree. So in a balanced tree, the height of the left and the right subtree of any node differ by no more than 1, right? Means the common type of the balanced tree includes you can include like AVL tree, red black trees. So this is a form of balanced tree, you can say, where all its children is available in the tree. But if you want to understand about the unbalanced tree, means the tree will look like this. This is not balanced tree. So this is balanced tree and this is unbalanced tree. Means it's all children having it's all you can say node having its complete children, right? So in this case, this is a balanced tree, means in the balanced tree the complexity will increase, right? The best case will happen, like we can say O log n, where we can say h is the height of the tree, right? You can say for the worst case, if this is unbalanced tree like this, right? So in this case, what will happen? It will become O of n if you're going with complexity, right? Like this, you can say time complexity, right here. So when we are talking about the space complexity, so it is become O of h due to the recursive call we are doing, right? You can see the first we have called the parent level, right? Now we are going with the left one, then we are going with the right one. Means space complexity will become what? O of h, means we will traverse all the nodes, right? So due to the recursive call stack, it becomes the space complexity is O of h, right? So now to ensure the better time and space complexity, you should consider using an iterative approach to avoid the overcome head of the recursive calls, right? Which, so when you will go with the iterative approach, these recursive calls will not happen, and due to that it will become what? O of 1, right? That you can see here. So this is an iterative approach to avoid the overhead of recursive calls that we have talked. So in this case, the space complexity become O of 1, right? And so that when a interviewer will tell you to will ask you to optimize the code, you should say, I can do through the iterative approach, and for that the space complexity will become O of 1, right? This complexity is it will become what? O of 1, right? Since we are not using any call stack for the recursion. So this iterative approach should provide a slight performance improvement, especially in the environment with the limited stack memory when dealing with a very deep trees, right? So let's suppose how we are going to do that, right? So here we are not calling any recursive, but this is iterative approach. So what we will do, we'll make the condition while loop. If root is not null, means this is your base case, right? And if the value will not match with the, if the root value is not matching with the search, right here. So in this case, what we will do here, I'm talking about here, right? So when the root is not null and the root value is not equal to the search value, right? In this case, what we will do, if root value is greater than x, means we have to provide what root is now what root dot left, and otherwise if it is if it is less than x means we have to go to right subtree, right? If this is not the case, we'll return root, means we match, we got the search at the root element, right? So it's very easy way to do iterative approach that you have to understand. So the interviewer asks you as a programmer to do implementation of a binary search tree, go with the recursive calls, recursive approach, and then he will ask you for the implementation. Then you can say iteration to the iterative approach, and that should provide a slightly performance improvement, because it is when we go with especially in an environment with a limited stack memory, or when we want to deal with very deep trees, then we can do iterative approach, and it will improve your complexity from O of h to O of 1, because we are not using the call stack for the recursion, right? Like that you can say, and you can move further. If interviewers say, are there any other approach that you can do through recursive or iterative for the BST, right? So what you can say, so in the context of searching in a binary search tree, right, there are multiple ways to do, but the two primary approaches are recursive and iterative approach that we have already discussed. However, if we step back, right, and we want to consider other potential solutions, so we could have you can say we can leverage different data structures, or you can say methods, if the binary search tree properties are not strictly required, right? Like we can do what we can do, convert in binary search tree to array, like we'll do convert the binary search tree, and we will convert the binary search tree to a sorted array, and then we can perform binary search, right? Like we used to do on the array, right? So this is generally less efficient in terms of space, and it doesn't make a use of the binary search tree properties. But we can say, like we can convert the binary search tree to the array, and array means sorted array, and then we can perform binary search, right? But we can also tell them that this is less efficient in terms of a space, and it doesn't make use of the binary search properties, right? But we can do by converting binary search tree to an array, right? Another approach we can say, we can do breadth first search, BFS, and although BFS is not commonly used for the binary search tree, like if we do BST search operations, due to its higher complexity, right, if we compare to the depth first search, right? So breadth first search we can use, but BFS is not commonly used for the BST search operations. But there is another approach other than the converting BST to the array. We can use BFS, right? But it is still an alternative approach. Then we can do the implementation. So BFS would require additional space for a queue. So let's understand how we can do the BFS approach. So this is a BFS approach that we can do. So in this approach, this is the base case, that if root is equal to null, will return null, right? That is the case. Other than that, what we will do, we can write an additional you can say space for queue, because we have to implement BFS. So we will take a queue of tree node, and we'll add a root on the queue. Then we'll go through while loop. If queue is not empty, we'll poll from the queue, and we'll say if node dot val is a search element, matches with the search element, means the element as at the root element or node, we can say, right? If it is not matching, right, then we'll check, then we'll first add onto the queue left, and then we'll add on to the right, and then we'll it will do recursive, it will do in the while loops, right? So it will check all the nodes left and right, like that, right? Because first come first serve, first we'll check in the left, then we'll check into the right, like that, right? So we are adding onto the queue left node and the right node, means left subtrees we are adding, then we are adding right subtrees, right? Means first we will check onto the root element, right? If root element is matching, then we return the root element node, root node will return, otherwise we'll pass what left subtree and right subtree, we will add on to the queue, and it will process through the while loop, right? So here we have seen that we have added additional space, that is what you can say queue, right? So we required queue as additional space, right, and that increases your space complexity, you can say, right? So if we'll talk about the time complexity and space complexity, right? So in the time complexity thing, the time complexity become what? O of n, let's suppose. Okay, so where n is the number of nodes in the tree. So this is because in the worst case you might have to visit every nodes, and so it become O of n, right? When we talk about the space complexity, right, so a space complexity is also O of n, right? So in the, this is in the worst case, right, because we required a queue that might hold all the nodes of the tree, right? So while we are doing VFS, right, while VFS isn't as generally used for searching the BST, because it doesn't leverage the BST properties to reduce the search space, right? So it is an alternative, valid alternative, and might be used in the specific scenario where breadth first search traversal is, you can say, needed, right? So however, for the specific task for searching a node in a binary search tree, the recursive, iterative approach, the depth first search are approach are typically most efficient, you can say, right? Either we can go with you can say recursive, iterative, or DFS, right? But BFS is not much preferable, right? Let's talk about then DFS, right? So in the DFS case, see, it maintains the stack, right, when we are going with a recursive call, but here we are maintains the stack using the explicitly, not internally, it implicitly, right? But when we are using DFS, we will do with explicit stack we are maintaining, right? So this is the base case, right? So what we will create a stack, then we will push root onto the queue, and then in the while loop we'll do pop, and we'll check the element. If the root element is matching with the search element, we'll return the node. Otherwise, what we will do, we know stack is LIFO, so first we'll push right element, and then we'll go with its child, right? So what we will do, right child, right, first left child and then right child, right, like that. So first we will add the right child, right, and then we'll add on the stack the you can say left children, so that on the top we have left one. So we'll go through first left, it will traverse, and then it will check in the right, so it will do DFS like that. Okay, so if we'll talk about the complexity, right, so similarly if we have n nodes are there, right, so the time complexity will become what? O of n, right? So this is in the worst case when we have unbalanced tree, right? When we are talking about the space complexity, right, so similarly we will get O of n in the worst case, due to the because stack holds all the nodes, right? Similarly, so this method mimics the recursive approach but uses an explicit stack to manage the nodes, and it avoids the limitation of the call stack, you can say. So this is still a form of depth first search, but yeah, you can say but it is more suitable for certain environment, or you can say constraints, right? So I think thank you for watching this video, guys. So if you have any doubt, and if you really like this video, and if you want more deep dive session in these topics, so please put some message or some comments that will encourage me to write again, you can say, to get this type of content, and I'll provide you more videos like this. So thank you for watching this video, and please give a suggestion and give me some you can say your inputs that will improve our channel. Thank you for watching this video.